All right, so I don't want to get into an in-depth discussion about the final today, but I thought I'd just show you what I gave as a review for the final last fall. So this will give you, let's see, I think our final's on Monday. And so if I just at least show you what to expect, that at least gives you about a week to be thinking about things rather than telling you on Wednesday. So let's just look at what I asked them to take a look at. This is a cumulative final, but again, it's not going to cover every single type of problem, but when we look at it, it's going to look like it, okay? I mean, just because we're going to go way back. Beginning, give you some conditions about a function. I ask you to sketch this. So, you know, limit from the left is doing this, limit from the right's doing this, blah, blah, blah. So that's the first problem there. Second problem, here's a function, and asking you to evaluate the limit from the left approaching 4, limit as you approach 3, limit as x goes to infinity. Identify any holes, you can throw that out. Identify horizontal asymptotes, we know how to do that. You let x go to infinity. So again, this is things you can go back and take a look at.
We can technically just use L'Hopital for that, right? No, we can't. Or what do you...
As long as you have 0 over 0, or infinity over infinity. Yeah, you can't. You have to have that though for that to. Because in this problem you're going to have some vertical asymptotes, so you're going to have places where you have fixed over 0, where you can't use L'Hopital. So from the left it's going to do something, from the right it's going to do something. Remember, it's either infinity, negative infinity, or does not exist. Third, some good old limits. Remember this? Common denominator, conjugate. L'Hopital probably won't work on that, or it'll get uglier. Like if you try and take derivative of the top of that, it's going to be very ugly. Number 4, here's another limit, x goes to infinity. This one is bounded over infinity. It's done, and then you're done. There's no work to be done in this problem. Because your numerator is sine function, and plus 1 is still bounded, and then the denominator goes to infinity. You can make that a very ugly problem, or you can just say bounded over infinity and be done. Use the definition of the derivative to find the derivative. So here's a nice little polynomial, and then this is the one where you have to do limit h goes to 0, f of x plus h minus f of x all over h. Yeah. And then find the equation of tangent line at a point. So now the good news is you do this using the limit. You get an answer, but we all know that the answer should be negative 4x plus 4. Like you can check it real easily, right? That's the good news.
It sounds so tedious.
It is tedious. Find where the tangent line to this curve is parallel to this line. And see, I don't say use the definition of the derivative here, which means you can use any method. So you just, well, again, we'll talk about it in more detail later. Here's an equation. Find the derivative implicitly with respect to time. So like, take derivative left side, derivative of v with respect to t is dv dt, blah, blah, blah. There's some product rule on the right-hand side. A spherical balloon is inflated in a way that its radius is increasing at a constant rate, blah, 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 blah. Related rates. A very simple related rate problem. It's not like, you know, the lights, you know, the light shining a person's wall. It's not a complicated geometry in this problem. It's a balloon, it's a sphere. Here's some derivatives. Find the derivatives. So this first one is a, you can't use the power rule. This is the one where you have to do log on both sides. Because you got x's both in the bottom and the top, exponent and the base. This is also a problem that tripped people up. I'll probably print this review out and let y'all have it. Derivatives with some chain rule here. Do you know derivatives of inverse trig functions? This one, I know it's hard to see, it's really small. Logarithmic differentiation. It's better to take log on both sides here and then do the derivative. So this is now starting to look familiar, hopefully. That's kind of like the problem you just did. Except there's some additional things here. You have these 5 identical pens that you're going to build, but you don't have to build fence along these edges because you're going to use the barn as the walls. So you really only have to build the stuff that's in blue. If you can tell, that's blue. It's blue and black. But anyway, there's another problem. Limits. X goes to infinity here. X goes to 0 here. This is one of those ones, again, where you're going to get one of those indeterminate forms. And you're going to use logs and L'Hopital. Common denominator. Because you get infinity minus infinity. And this is where we get into what we started talking about last class. Antiderivatives. Antiderivative. Okay? So that gives you some, at least a perspective, yeah? That give you some perspective on what's to come. All right, so I want to talk some more about antiderivatives. So, do you have your formulas with you? Your formula sheets that I've asked you to bring? Look at reference page 6. Yeah, it's 6. Do you have yours?
Yeah.
No? No? Well, just look off someone else's. If you don't have it, just go roll your chair over to someone so you can just see what I'm talking about. Everyone got reference page 6, or someone near them have it? All right, on reference page 6, you will see a list of basic forms of integrals, numbers 1 through 20. You see those? So let's take a look at the first one. I want you to completely ignore the first one for now. There's an entire section dedicated to that formula. It's called integration by parts. That'll come in Cal 2. But on number 2, this is actually a formula for taking the antiderivative of like x to the 4th. Now we did this last class, didn't we? Yeah. And we said that this would be, what did we say about the power? It has to be one more, and then we'd always have to get rid of the 5, so we'd have to put 1/5 out here, right? Then plus some constant. Y'all remember this from last week? I know it's been like a long weekend, yes? All right, so that formula right there is a generalization of this rule. It says, look, if you have x to the n, then your answer is going to be, they use u instead of x, right? Okay, so they say your answer is going to be x to the n plus 1 over what? N plus 1 and then plus c? Okay, another way of writing that would be 1 over n plus 1 times x to the n plus 1 plus c. So you see, like, in this problem, n is 4 here, right? So this is 1 over 5 is the same as 1 over 4 plus 1. 4 plus 1 is 5. So you're going to have 1/5 out front, x to the 5th. Understand? Plus c. That's the general formula for finding antiderivatives of powers of x. Now there is one other thing they have there. They put what? N is not equal to -1? Because what if n is -1? That was x to the -1, right? dx. That's the same as asking you what's the antiderivative of 1 over x, right? And that's the natural log, right? Now is that on here? Ah, yeah, it's number 3. Do you see where it has du over u? That's the same as writing dx over x. Understand? And they're saying that the answer to that is what? Natural log of what? Absolute value, okay? Now that's something I did not mention last class. I want to mention that now. That's why I'm having you look at it. From here on out, if you're taking the antiderivative of 1 over x, the antiderivative of that is the natural log of the absolute value of x. And that's because, remember, in a logarithm, you cannot have negatives, right? So we do an absolute value in there. Acceptable? All right. And then what about the next one? Antiderivative of e to the u is what? E to the u plus c. Does that make sense to you that it would be that? Yeah. Yes? All right. How about the next one? Whoa. Antiderivative of a to the u. So let me give you an example of that one. I know it looks bad, but look, let me do it this way. Let me ask you this first. What if I gave you 4 to the x and I asked you for the derivative? And I'll put something below this. What about e to the x? What's the derivative of e to the x? Itself, right? E to the x, right? That's derivative. But when it's not e down here, it was something special. We had to say 4 to the x itself, good, times natural log 4, right? Okay. So when we do the antiderivative of something like this, like if I say what's the antiderivative of 4 to the x dx, well, it should be itself, right? It should be itself. Okay, so 4 to the x. But if I take the derivative of this, I'm also going to get a natural log 4 to pop out, right? So I want to undo that, so I divide by natural log of 4 plus c. Do y'all kind of see that? Right? This is a constant. This is a constant. So you could look at this as being 1 over natural log of 4 times 4 to the x. If I say take derivative of this right here, the constant's going to come for the ride. Derivative of that is this, right? And the natural log 4s will cancel out. Yeah? So the formula, what does formula 4 there, or 5 say? It says if you have anything to the u, I'm going to say x though, that the antiderivative of that should be itself, right? Divided by what? The natural log of a plus c. Good or not? Yes? Okay, and then we keep going. Okay, what's the antiderivative of sine? Number 6. Negative cosine. Right? Because what's the derivative of cosine? Negative sign, but you don't want negative sign, you want positive sign, so you have to say negative cosine. Number 7, what's the antiderivative of cosine? Just sine, right? Because the derivative of sine is cosine. So that makes sense to you? Number 8, antiderivative of secant squared is tangent, because we know derivative of tangent is secant squared. And then numbers 9, number 10, number 11, number 9, 10, 11 are all coming from what we know about the derivatives of all those trig functions. Tangent, cotangent, secant, cosecant. Because we know derivatives of those, we can undo their derivatives. Now, once you get to formulas 12, 13, 14, and on, the rest of those, well, take Cal 2, we'll discuss those in Cal 2, all right? And then you have formulas 21 through, well, there's reference page 7, and reference page 8, and reference page 9, and reference page 10, which you don't have those, right? No. These are all formulas for antiderivatives, for common antiderivatives. And you could probably find a textbook, hundreds of pages thick of just formulas for integrals. Because it's a much harder task. Understand? There's a lot more formulas for antiderivatives than there are derivatives. Now switch back to reference page 5. Reference page 5 had 36 formulas for taking derivatives, and that's pretty much it. There's really no other formulas that you need for derivatives. You've got product rule, quotient rule, chain rules all there, derivatives of logs and exponentials, your trigs, your inverse trigs, your hyperbolics, your hyperbolic inverse. You got it all there, all right? That one page covers all of your derivatives. Antiderivatives, 5 pages is not even enough, all right? So in my classes, I will allow you to have reference page 6 on your tests. You can use any of those formulas. All the other ones, well, you're going to have to work. You're going to have to work for those problems. So, all right. With all of that in mind, with that reference page in mind, I'd like to practice some more antiderivatives now. And do you remember we were doing substitution last class? We just started looking at substitution. Let's hold off on substitution for now. I just want to work on just regular old antiderivatives. All right, so let's start with let's find the antiderivative of x squared minus 3x plus 4 root x over x cubed dx. We may have done one similar to that last class. Any ideas? Split it up. Very good. You do not try and do this by just doing each one separately. Okay? You don't just do, oh, antiderivative this, 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 and this all separately. Because you have a quotient there, and it just doesn't work that way. The best you can do right now is to split this up into 3 separate terms, like this. I'm going to rewrite the root x as x to the half. And I'm doing that all in keeping in mind that I'm going to be using properties of exponents now to clean up these powers. So we take the power on top, we subtract the power on the bottom. So what is this first term really going to be? 1 over x. Okay? And then the next term. Negative or minus what? 3 over x squared, right? 3 over x squared, but I'm going to write it this way instead. 3x to the negative 2. Now why did I write this one as 3x to the negative 2, but I didn't write this one as x to the negative 1? Because I know this is a special one, right? 1 over x is a special one. Any other powers of x, I can use that rule, that power rule that I gave you, formula, whatever, what, 2 on the sheet? Was it 2? Yeah. Formula 2. Okay, what about my last term? This is going to be plus 4x to what power? Five halves. Minus 5 halves. Okay. Right? We're doing 1/2. We're taking away 3, which is 3 over 1. That's 1/2. Minus, minus 6 halves. And then minus, hey, easy. I messed up on one of my homework videos. What did I put? The square root of 1,000 was 100 or something? Yeah. I convinced you, huh? I did correct it though, right? At the end, but way at the end I realized it. Okay, yeah. Hey, it happens. Okay, we good? All right, so now what we'll do is we'll apply the rule. And the reason we can do it now is because we have 3 separate terms, right? We no longer have like something over something. It's 3 separate terms. So the antiderivative, once we do the antiderivative, this thing which we call the integral sign is going to go away. The dx is also going to go away. And I didn't talk a lot about the dx last time. I told you just it's there, right? Think about it. Think about the dx as really being the derivative of x with respect to x. What's the derivative of x with respect to x? It's really a 1, okay? But the reason why we put it there is because when we make substitutions later, like I showed you last class, that thing at the end is no longer 1. It's something else, right? So when we actually do the integration, all this symbol and this are going to go away. And I like to just tell students, look, if these two are going to go away, what's going to appear over here is going to be the plus c. All right? Because people always ask me, like, what happened to this and what happened to this? Nothing. We're finding the antiderivative. That's it. But if you want something to happen, just say that this and this turn into plus c, so you don't remember or don't forget plus c. All right. So antiderivative of 1 over x is natural log of the absolute value of x. All right. How about this one? Minus 3 is a constant, comes for the ride. So I'm just going to put minus 3. Now times, this is x to the n. So the formula says I'm going to add 1 to that, right, which is negative 1. So I'm going to have x to the negative 1 here. But then out front, I'm going to put 1 over negative 1. So whatever this power is up here, you're going to put 1 over it in front. Yeah? And double check it real quick. If I bring this out, if I take the derivative right now, negative 1 comes out, that turns into a 1, doesn't it? And then I subtract 1 from that, I get x to the negative 2. So the derivative of this right here would be x to the negative 2, and then I have a negative 3 out front. So it would give me what I want. All right, next one's a little bit trickier. We have plus 4 times, I'm going to, again, leave myself some space here, x, and then I need to add 1. I need to add 1 to negative 5 halves. Negative 3 halves. So I'm going to put negative 3 halves here. And then out here, 1 over negative 3 halves, which is really going to turn into negative 2/3. All right? But I just want to stress, like, it's 1 over a fraction, it's going to flip up. But I'm going to have to rewrite this anyway. Plus c. So this is going to be equal to natural log absolute value of x. What's this together here? Plus 3. Plus 3 x to the negative 1. Right? Okay, if I write it like that. This one right here, when I put this together, this is really 4 times negative 2/3, right? Which is negative 8/3. So I'm going to write negative 8/3. Why am I writing it like that? Negative 8/3. Because this, because it's a negative power, I'm going to drop it down. It's going to join the 3. And it's going to be x to the 3 halves. Plus c. Now, it would not be incorrect to leave this as plus 3 x to the negative 1 and leave this as minus 8/3 x to the negative 3 halves. That would be fine. I'm just showing you, like, that's probably what the book would have. And the book might even go a little further, because that right there is really x root x. Right? Because that right there is the same as x cubed square root. And you can pull out 1x. You'd be left with 1x inside. And so that would be that. So I'm just showing you, what you may see. All right, what do you think? Huh? This looks exactly like this prop. I keep on thinking this is my mouse. Okay. This looks exactly like the problem I gave on that final review. Look at that right there. You see that? It's very similar to that idea. Split this up into 3. I'm just saying I've tested this before. And, I'll have people do all sorts of weird things with that. But, okay. Let's do something else. Let's do... Find the antiderivative x cubed plus x minus 1 squared dx. So you're thinking u substitution here, maybe. I'm not going to do u substitution yet, so I'm kind of giving you a hint right now that it's not u substitution.
Do like backward table, like so.
Maybe. The way I want you to think about it is right now, the only thing you can take the antiderivative of, the only thing you know how to do right now, is powers of x, or possibly like 1 over x where it's natural log, or secant squared, you could take the antiderivative of that because you know that that's tangent, those types of things, right? So if that's all we have in our toolbox when it comes to tackling these things, then you've got to get this to look like a power of x. And the problem is you've got the squared there, right? If that squared wasn't there, you would just do each one separately, wouldn't you? But the squared's there. Let's just multiply it out then. Let's just multiply it out. Let's just do x cubed plus x minus 1 times x cubed plus x minus 1. And let's just, unfortunately, we have to multiply that. But that shouldn't be too big of a deal. Let's see. Remember how to do this, right? 3 terms there. Then you go to the second one, you do 3 terms again. 3 multiplications. Here, here, and here. And then you go to the last term, the 1, negative 1, and you multiply that through to all 3. You're going to have a total of 9 multiplications that you have to do here. So I'm getting, what, x to the 6th first, then plus x to the 4th, bless you, minus x cubed. So that's what I get when I multiply these black multiplications. Then the blue multiplications, I get what? Plus x to the 4th, plus x squared, minus x. And then the negative 1 gets passed through, negative x cubed, minus x plus 1. Now I could now do 9 antiderivatives, couldn't I? But I could also collect like terms. So I'm going to collect like terms first. So this right here is going to equal antiderivative of, let's see, x to the 6th. I just have one of those. No x to the 5th. X to the 4th, I have 2 of them. X cubed, negative 2. X squared, just 1. X's, minus 2. And constants, plus 1 dx. It's all right? All right, let's see how fast we can do this. Now you want to get to a point where you get quick with this. That takes some time. The only way you can get quick is if you practice, all right? So section 4.7 gives you an opportunity to practice. I have not posted any solutions for 4.7. Let's see, what is the antiderivative of x to the 6th? So power goes up 1, x to the 7th, and I need a 1/7 out in front. 1/7 x to the 7th. All right, that's good. What about the next one? Ignore the 2 for now. X to the 5th, a 1/5 in front. 1/5 x to the 5th is the antiderivative of that. But when I have a 2 out front, it's really going to be 2/5 x to the 5th. All right, negative 2, ignore it for a minute. What's the antiderivative of x cubed? 1/4 x to the 4th. 1/4 x to the 4th. So I hit that with a negative 2. It should be minus 1/2 x to the 4th. Am I doing this too fast, or are y'all catching on? You understand? What about this one? Antiderivative of x squared. 1/3 x cubed. Antiderivative, ooh, okay, cover up the negative. What's the antiderivative of x? 1/2 x squared, right? 1/2 x squared, but then you have to multiply it by negative 2. So just minus x squared? And finally, what is the antiderivative of 1 with respect to x? Just x plus c. All right, there you go. Would you agree that if these are nice integer powers, positive integer powers, the antiderivatives are pretty clean?
Yes.
It only becomes really complicated when these are fractional powers or negative exponents, because you have to be careful when you're adding a number to a negative number, right? You just need to be careful. All right, now, how would this problem look if I change this to like 20? Well, then we wouldn't do it this way, okay? We wouldn't. Could you multiply that out times itself 20 times? Sure, I mean, if you had a week to do it and you had nothing else going on, you could do it, right? You might make a mistake in there, but yeah. Well, you check it by taking the derivative, right? And you need to get that back. So look, the point is that there are certain things we can handle at this point, even though they look like we may not be able to. If we're willing to do the algebra, a little algebra first, we're still in control of this situation. But it's very easy for it to become nasty. All right? All right, so let's now think about something we talked about in the past when we were first talking about derivatives. And that's, remember that if you start with the function, right, you take its derivative and you get f prime, right? I'm going to put diff here for differentiation, right? You get f prime. You take the derivative again, differentiate, you get f double prime. If this was a position function, then the derivative was the velocity function. Do y'all remember me talking about that? Yes? Yes? I see like 1 or 2 yeses. The rest are, it's unknown still. If you take derivative of velocity function, you get what? Acceleration function. So that we should be able to go backwards then, right? If somebody gives us a second derivative, we should be able to go backwards to recover what f prime was by doing integration, right? And we should also be able to go back to f if we integrate. There's going to be a problem though. What's the problem? You have the plus c, right? So when we integrate, when we start here at f double prime, if I give you the second derivative of a function, to go back and exactly find me where it came from, you're only going to be able to do it within a constant. You're going to be off by a constant. You're going to give me a family of functions, and then if I ask you to go back from there, it's going to be really impossible because you have an infinite number of functions to go back from. So maybe there's still a way around it. So I'm going to give you a problem the way it would appear in the book. All right? So let's say that I give you the following. I give you that f double prime of x is equal to 8x cubed plus 5. I also give you that f of 1 is 0, and I give you that f prime of 1 is 8. That's all given to you. The instructions here are for you to find what f was. Give me f. So we're starting at f double prime. I want you to go all the way back to f, and I gave you some pieces of information that might help you find f. So what can you tell me about f prime? It has to be the antiderivative of f double prime, right? It's the antiderivative. So f prime, I'll put f prime of x, should be equal to the antiderivative of 8x cubed plus 5 dx. Do we agree with this? We're going backwards on that chain. And can you tell me what the antiderivative of that is? 8 times 1/4 x to the 4th.
So
2 x to the 4th
plus
plus
5 to the
5x plus c. And we'll do a quick check. What's the derivative of this? 8x plus 5. Okay, good. So we've got the right thing, right? We're off by a constant. Okay?
Now f is.
We know what f prime is almost, right? We're off by a constant.
Yeah.
But, right? They tell us something. They say, hey, guess what? When you plug in 1 into the derivative, it should spit out 8. Right? So if I come back over here and I rewrite this, I'm saying this is equal to this. I know f prime of x is equal to 2x to the 4th plus 5x plus c. But if I plug in 1, right? If I plug in 1 for x, what would I get here? 2 plus 5 plus c. I don't know what c is, right? I don't know what c is. C, that when I do that, it must be what? 8. You understand what I just did? So if this is just 7 plus c is 8, solve for c, you get c is 1. So this means c is 1. That means I actually know exactly what f prime of x is. I'm not off by a constant anymore. So I can write this. So, comma, f prime of x is exactly 2x to the 4th plus 5x plus 1. That's what f prime is. Questions? Now what?
Now do the derivative.
Go back again now, all right? So now what I can say is f of x should be equal to the antiderivative of that. So I'm about to repeat the process, right? And what is the antiderivative of each of those three terms? So 2/5 x to the 5th 5 halves x squared plus x plus c, right? Plus c. Now, we already used c in this problem, didn't we? I don't want anyone to confuse the two c's. So I'm going to call it something else. And the most common thing we use is capital D, right? We just use capital C. Let's use capital D. Everyone understands capital D is just a constant. Is that all right with you? Yeah. Okay. So we almost know exactly what f of x is. Almost. We're off by a constant. But again, they've given us this nice piece of information, haven't they? They've told us that the original function at 1 should spit out 0. So if I plug 1 into this, I get 2/5 plus 5 halves plus 1 plus d, but that must equal 0, right? And so now I can solve this for d. So let's put these together. Uh-oh, common denominator? Ooh. 10? Why don't we just multiply both sides of this equation by 10? Can we do that? Let's multiply this by 10, this by 10, this by 10, this by 10, this by 10. What would your equation become? This times 10 would be what? 4. This times 10? 25. This times 10? 10. This times 10? This times 10? 0. So what are you getting over there? 35, 39? 39. So I've got this. Put it right here. 39 plus 10d is equal to 0. So move 39 over, divide by 10. Yeah? D is negative 39/10. So my original function, I've got it here now. My original function, f, is, where was it here? 2/5 x to the 5th plus 5/2 x squared plus x minus 39/10. That's the original function right there. What do you think? Now, let me show you something. Did we talk about gravity in here last time? No? We didn't talk about gravity. All right. So let me show you something really cool. Okay, yeah, I know. Not that one. All right. This is just like I had here a second ago. If we start with some function f, we take its derivative, you get f prime. You take its second derivative, you get the second derivative, right? But if that first function is a position function, and specifically straight line motion, then its first derivative is velocity and its second derivative is acceleration. I know we discussed that before. But if you look at what we've just did in the previous problem, this means that if you know the acceleration function and maybe a couple of pieces of information, right, just a couple of few little things, then you should be able to go all the way back to the position function from just knowing acceleration. Now, before I actually show you the really cool thing, I want to kind of illustrate in pictures what we just had. In the previous example, I gave you f double prime, didn't I? And it was some cubic function. Right? So whatever it was some cubic function. I'm just making this up. This was f double prime. We went backwards from that, but I had to have a piece of information, didn't I? I had to have that f prime of 1 was 8. Didn't I have to have that? So that meant that at 1, 8, this point lived on f prime, right? So if you look at visually what you were given the graph of the second derivative, you were given 1 point on the first derivative, and if we go back to the original function f, you were given what? F of 1 was 0? You were given 1 point here. So if you look at it this way, then if somebody gives you a second derivative, right, function, to get all the way back to be able to draw f, or exactly what f is, you need two pieces of information. You need 1 point on the derivative, and you need 1 point on the original function. With those two pieces of information, we're in business. All right? We can recover that function completely. Okay? Yeah? Okay. Now, how many of you, I know at least one of you who had me for college algebra, might recall this formula. Hopefully your instructor at some point showed you some version of this formula. It may have looked like this. D of t equals negative 16t squared plus v naught t plus d naught. It might have also looked like this. H of t equals negative 16t squared plus v naught t plus h naught. Raise your hand if you've seen that. 1, 2, that's it? Physics class? No?
You got into a huge fight with that Navy guy over the knots.
Oh yeah, that's right. About spelling knot.
Well, it's not V naught, it's H naught. Then you got rid of that.
Okay, so look. These are the equations that we use on Earth. Okay? If you have a falling object on Earth, all right, so if you drop something on Earth, then you can figure out where it's going to be at every point in time. And this is the actual function. So there's a couple things you have to know about this. This d naught is the initial height. So if I drop this thing from 30 feet, I would put a 30 here. All right? And then this right here is called the initial velocity, which means when you drop something, you can either just drop it, right? Or you can shoot it, like throw it, and then it would get there faster, right? Or you could actually throw it up and then it would come back down, right? So that speed that you give the object at the beginning, either up or down or just dropping it, is this number right here. So if you throw it up in the air, this is a positive number. If you throw it down, it's going to be a negative number. And if you just drop it, that's 0. Okay? Initial height, initial velocity. Got it? This number right here actually comes from the fact that we're on Earth. And on Earth, well, there's something that's always going on Earth. Gravity, right? So let's see if we can figure this out. All right. What is gravity? Gravity is you may have heard like negative 9.8 meters per second per second. If you convert that to feet per second, it's about 32 feet per second, right? Gravity is an acceleration, right? It's an acceleration. It gives you the rate of acceleration of something. So what I'm going to do is I'm going to start with gravity on Earth, all right? Gravity is an acceleration function, a of t. I'm going to call it a of t for acceleration. On Earth, it is negative 32 feet per second. All right? And the acceleration of gravity is independent of time. If I drop this thing, right, it's going to start accelerating. Its acceleration is constant. Its speed's not constant, but its acceleration is. So that's on Earth. If we're on a different planet, this number's different. If we're on the moon, it's different. If we're on, well, Mars, whatever. It's a different number, right? So let's say everyone says, all right, great, that's the acceleration function on Earth. What's the velocity function then? Well, the velocity function would be the antiderivative of this. What's the antiderivative of this? With respect to t, not x. Negative 32t, right? Negative 32t plus what? Some constant, right? Some constant. Now, I don't give you any point here, do I? I'm not giving you some initial point. So let's think about something. What would the velocity at 0 be? What would the velocity at 0 have to be? It would have to be c, right? Wouldn't it? So why don't we call this c something very special? Why don't we call it, well, the velocity at 0, right? Why don't we call it v naught, the initial velocity? So we just call that c something now. Make sense? V naught. You all okay with that? All right, so really right now, this is where we're at. We're at v of t is equal to negative 32t plus v naught. V naught is really c, but it's special in the sense that we know that that's the starting speed of the object. Starting speed because I replaced that with 0. 0 is times 0, that's when we start. Make sense? Okay, give me the position function, which I'll call d of t. D meaning distance. D of t will be the antiderivative of this with respect to t. Negative 32 times 1/2 t squared. Negative 16t squared. Plus, this is just a constant, right? What's the antiderivative of a constant with respect to t here? V naught t. Plus some constant because we're integrating, right? Let's call that capital D. All right? Again, I don't know what capital D is, but if I take a look at what D of 0 would be, D of 0 would be where I should be, my position at time 0, right? And if I plug 0 in here, it kills off these, right? And I'm just left with D. So why don't we give that a fancy name? D naught. Why don't we call it D sub 0? And that'll be our initial position. And that means that our position function on Earth under the force of gravity should be negative 16 t squared plus v naught t plus d naught. And that's where that formula comes from. All you had to know was the acceleration of gravity. Now, we took some things out here. We neglected air. Air resistance does complicate things because then your acceleration function is not a constant. Your acceleration function then depends on a lot of different things. A lot of different things. So, but we start with something like this. This is good enough for a lot of basic applications. All right, so I think that's pretty amazing. That all you need to know, in order to know exactly where an object is at every point in time, right? This function will give you where something is at every point in time. In order to know exactly where something is at every point in time, I just need two things from you. Please, just tell me its speed at one point and give me its position at one point. If you give me those two things, I've got it. I can tell you where it was at every point in time. Does that seem amazing to you? It seemed amazing to me when I first learned it. It's like, it seems like you would need to know more, right? But you don't. Okay. Hopefully that gives you some value to how antiderivatives could help us recovering position functions. Let's do one more, and then we'll talk substitution. So what about this? Yeah, this one looks exciting. F double prime of t equals 2e to the t plus 3 sine t. And I'm going to give you that f of 0 is 0 and f of pi is 0. No, they're not both f prime. Or no, they are both f. I'm sorry. I did not accidentally forget the prime. I'm glad you noticed that because I was about to point that out. All right, so let's go for this. What can you tell me about f prime? F prime of t, right, we're using t here, is the antiderivative of 2e to the t plus 3 sine t dt. See, I'm using dt instead of dx. All right, how about this? Two separate terms, I can do them individually. 2 times something, 2 will come for the ride. Antiderivative of e to the t is itself, right? So we have no more integral sign, 2e to the t. The 3 is going to come along for the ride, plus 3. What's the antiderivative of sine? Negative cosine, right? So this becomes minus 3 cosine t plus c. I'll do a quick check. What's derivative? This comes from ride. Derivative e to t is itself, so this is just 2e to t. Yes. Negative 3 cover it. Derivative of cosine t is negative sine t. And then the negative and negative become plus. So yes, I've got it. All right, so I'm happy I can move on. Now this is where we used in the last problem, I used a piece of information over here to figure out what c was, right? Yeah. I don't have that information. But I have two pieces of information about f, don't I? So what I'm doing is I'm going to try and get back to f right now. So if I try and go to f, I'm going to integrate antiderivative of this. 2e to the t minus 3 cosine t. But don't forget, plus c is there also, right? You don't know what c is, but you need to account for it. Plus c dt. So what is the antiderivative of 2e to the t? 2e to the t. What is the antiderivative of, I'll cover up the negative 3 for now, of cosine t? What's the antiderivative? Just sine, right? Just sine. And then the negative 3. So negative 3 sine t. What's the antiderivative of a constant? The constant, no, that's a derivative. The constant times t. Right? If this was 5, wouldn't you say 5t here? This is c though, so you're just going to say plus ct. It's some constant, I don't know, times t. With me? What's still out here though? Plus some other constant. I'm not going to call it c though, I'm going to call it d. This is what f of t is. So we're off still, right? There's two things I don't know about f. I don't know what c is and I don't know what d is. However, I have two pieces of information, don't I? So let's see if we can use that information to help us get c and d. So I'm put here, but f of 0 would mean, plug 0 in for t here, be careful. 0 in for t. E to the 0 is 1 times 2, so we get 2. What's sine of 0? 0, so that's gone, right? That's gone. Plus, plug in 0 here. 0 plus d, so you get 2 plus d, right? End of the day, that's what you get there. That must equal what? 0, right? So that means 2 plus d must equal 0, which means d is negative 2. Agreed? Great. I know what d is now, don't I? I think right now, well, yeah, we could plug it in. We could right now just say, hey, look, we know that that's, what, minus 2 now? To get c, let's try and use the next piece of information, which is f of pi must also be 0. So let's plug in pi. Ooh. 2e to the pi is 2e to the pi. All right. Minus 3 times sine of pi is 0. Plus c times pi, so plus c pi, minus 2, right, must equal what? 0. Must equal 0. Ooh, our c is going to be pretty ugly. But everything there is a number except c, right? C is the only thing that's not a number. So what I have is 2e to the pi plus c pi minus 2 equals 0. I'm going to isolate c now. So I'm going to add 2. I'm going to subtract 2e to the pi. So I get c pi equals 2 minus 2e to the pi. And then finally what? Divide by pi. So c is equal to 2 minus 2e to the pi over pi. D was a lot nicer than c, huh? D was a lot nicer than c. So I'm ready to write my final answer, which is the function f. The function f is f of t equals 2e to the t, what was it, minus 3 sine t? Was that it? Yep. Okay, and then it was plus c times t, so plus 2 minus 2e to the pi over pi times t, and then plus d, but d is minus 2. There's your function right there.